Hello, everyone, and thank you for joining us today for our Addressing Design Challenges and Solutions for Sewer and Underground Storage webinar. Before we start today's presentation, we would like to cover a few housekeeping matters that will ensure you have a good experience. We have placed all phones on mute to cut down on background noise and to ensure everyone can hear the presentation. At the conclusion of today's webinar, we will provide information on how to obtain PDH credit for today's presentation. Our webinar today is scheduled to last for 1 hour and will include a question and answer period. If you have a question, please type it in the question box at any time. Today's webinar is hosted by Andrew Jenkins and Rian McCaslin. Andrew Jenkins holds a Bachelor's of Science degree in engineering from Missouri University of Science and Technology. He has 24 years of experience in civil, mining, and petroleum engineering industries. For the past 18 years, Andrew has held multiple leadership positions at Contech. Most recently, he was the Director of Plastics Division and Director of Wastewater Treatment. Currently, Andrew is the Area Pipe Manager for the Great Lakes and Atlantic region. Ryan McCaslin is the Drainage Area Manager for Contech's Great Plains and West region. McCaslin has been with Contech for more than 20 years and has experience in manufacturing, construction, and marketing for various civil engineering construction materials. Most recently, Ryan has focused on wastewater, stormwater, and irrigation conveyance and pipeline rehabilitation. Ryan holds a bachelor's degree in civil engineering from North Dakota State University. Now I'll turn the presentation over to Andrew to get us started.
Thank you, Jill, and thank you for everyone for attending. We have a really big group on here today, and we all appreciate that. For those of you who don't know Contech, welcome. For those who we've worked with before, thanks for coming back and joining us. Contech is has been around for a long time, over 100 years now, and we offer a full suite of site solutions that you can categorize kind of in 3 buckets. First, the stormwater management division, which includes treatment systems and underground storage. Our pipe division, which includes culverts, drainage, storm sewer, sanitary sewer, and reline products. And our structures group, which includes bridges and erosion control type solutions. We've been around for a really long time. We cover the entire United States and Canada, and we're here to help solve your civil challenges and your projects. So we have limited time today, but if you want a more in-depth presentation on any of the topics that or products that we offer, please let us know. We can come in and be very specific and custom to you and your needs. And I always want to remind folks that Contech is more than just a provider of products. We have a very talented, industry-leading team of engineers, professionals all across the United States. So again, we're here to help. We have a lot to offer in the form of engineering support, CAD, all sorts of things. And if you've never been to our website, go to Contech ES, Engineered Solutions, that's what ES stands for, contechES.com. It's a very well done website, and there's tons of information. So let us know how we can help. So today's topic, we're going to talk about sewers, mostly sanitary sewers, and underground storage. There's a growing need for combined sewer overflow and sanitary sewer overflow underground storage. So we're going to focus in on that. We're going to do a quick intro to that segment of the industry, and we're going to talk about what we think maybe the top 3 design challenges are, including service life, structural integrity, and then we're going to talk about some project constraints and other design considerations, and then we're going to conclude. Before we get into that, though, I do want to set up where we're asking you and your mind to go. Let me forward this forward one. There we go. And that is large diameter sewers. What's in the offering? The mouse is acting up today. I apologize, everyone. So large diameter sewers. I want to kind of make sure that the audience today puts their brain into more along the lines of trunks and interceptors and outfalls. What we're trying to talk about is not your typical day-to-day sanitary 8-inch and 10-inch mainline and collecting pipe type systems. We're talking about the bigger stuff, and there's a difference in that design world, so to speak. And for the most part, most interceptors, trunk lines, things like that, tend to be very long runs, much deeper than your traditional collection system that's out in the roadway. Very straight, very few taps or laterals per mile, so to speak, in this compared to 8-inch. Rarely designed full, 50%, 70%, very commonly designed for its flow rate. So this is where we want to kind of begin with. And what we noticed over a decade ago was there was not a lot of solutions for this, and the challenges that a long, deep, straight, corrosive environment type product might need. There's really just three main types of products being used in this segment. The first one being reinforced concrete pipe. We all know that, I believe. Everyone on this webinar probably has obviously dealt with RCP in the past and will do so in the future. Very large size range, up to 144 inch. But in this world of deep sewer, you tend to have to go in the larger or the higher classes as far as the RCP class. There was various classes, various thicknesses for the structural requirements. It is a rigid design, 6 foot to 8 foot lengths, a standard in the industry, really. There is some chemical resistance issues, sometimes with that and joints. There's a joint every 6 to 8 feet, but it's been around for a long time and will continue to do so. So there's option one. Option two, ductile iron pipe. Now, ductile iron is limited to 64 inches. It is not a rigid per se pipe. It is considered semi-rigid. Up to 20-foot sticks. Very good product, been around for a very long time. Also has some issues with chemical resistance. Quite often in the sanitary world, it has a liner, and sometimes it's even bagged for external protection. And then something that's been growing more and more over the past couple decades into this market space is fiberglass pipe. Fiberglass, again, has a very large diameter range. It is considered a flexible thermoplastic as far as design, so it's not rigid. It does have some limitations in its deflection requirements as far as the short-term deflection, but is a very good product and inert to the corrosive environment of sanitary sewers. So that's what's been offered today, or has been in the past, I should say. Contech brought steel reinforced polyethylene into the mix over a decade ago. And many of you might not have heard of SRPE. Maybe you have, maybe you haven't seen it in this segment of the civil engineering infrastructure world. But I just did a quick chart to show, okay, so here's how they stack up. RCP up to 144, ductile iron 63. One of the things I wanted to note is, as we show through this presentation, SRPE is a very efficient design product, and you can see that in its weight comparison, pounds per foot. For this example, shows 60 inch. 1,400 pounds for a stick of RCP or per foot, and then SRPE is 43 pounds. So there's a big discrepancy there, and it's really because of the very efficient design of the Duramax pipe. So we're going to talk about the design challenges of predominantly this sanitary sewer environment, and think through as we go through this, how have you addressed it with RCP? How have you addressed it with fiberglass? If you have questions, please send them to us. We'll either answer them in real time today, or we'll answer your questions after the webinar. But feel free to send us notes and let us know what you're thinking as we go through this. So we're going to move into the top 3 challenges here in just a second. but I believe we have a poll question first.
That's right, Andrew. Here's our first poll question. What large diameter sanitary sewer challenges do you face most frequently? Service life, hydraulics, shallow slopes, taps and connections, or structural integrity? I'll give you some time now to mark your selections. Just a reminder, if you have a question, type it in the question box and I will ask it at the end of this presentation. I'll give you a couple more moments to make your answers. They're rolling in. I'll give you a couple more seconds. Okay, well, thank you for participating in our poll. Looks like 14% say service life, 11% say hydraulics, 43% say shallow slopes, 17% says taps and connections, and 14% say structural integrity.
Well, that's very interesting, and my brain's already thinking through, shallow slopes. That's a good one, and we're not covering it in this, but I could say that, shallow slopes, a couple things going on there. One, you're probably very deep, and so you're already deep, and instead of going any deeper, which becomes very problematic for the design, you're just trying to not lift the gravity sewer as often as necessary. That's one. Two, that does affect the hydraulics, which we are going to cover, and also has some play in the corrosive environment as well, especially when it comes to moving that flow and the biofilm that could be created. So that's a good segue, actually. So the number one hit was shallow slopes. We appreciate everyone participating in that poll. So segue into biofilm. The service life and sanitary sewers in general it's really mostly about the corrosive nature of the environment itself. There's not a lot of abrasion concern when it comes to pipe types, but the corrosion is predominantly driven by hydrogen sulfide gas, H2S. If you're new to this part of civil, hydrogen sulfide gas is created from the biofilm buildup or the slime layer, and that tends to get worse the more rough the surface is. Sometimes with concrete pipe, it can get kind of rough, and it'll build up over time. And as that hydrogen sulfide gas is emitted, it collects into the crown of the pipe, where it interacts with the condensation and creating sulfuric acid. So H2S, it's that rotten egg smell. It's toxic. It's a health hazard for people working in that environment, can be. So it's nasty stuff. That sulfuric acid breaks down the pipe material and creates what's commonly known as crown corrosion. So this is a big deal in the industry. It's a $1 billion industry dealing with this issue and managing through it. It's also a big deal for manhole structures, etc. So Contech's answer for this is the design of a plastic type of pipe. And in doing so, Contech chose to go down the path of a very innovative design concept, which combined steel with polyethylene. So what we're looking for here is how can we build a very large diameter material for very deep burials in a highly corrosive environment, and that's where Duramax came up. So this is not a standard plastic pipe, as I've mentioned. It's combining all the right benefits of structural steel reinforcement with a pressure-rated HDB polyethylene. HDB is a hydrostatic design basis pressure-rated resin. So it's the same resin you get with solid-wall polyethylene. And when you fully encapsulate a very robust 80 KSI steel and you helically wind it into a pipe, you get a very unique and good solution for exactly this type of environment, allowing for very heavy loads, very deep burials, and key here is we get into the very large or ultra large diameter sets. That's what the steel allows us to do. is grow that diameter from 30-inch all the way up to 120-inch in diameter. So I don't think I need to spend a lot of time on the environmental stability or the corrosion resistance of polyethylene. I think this mouse is very touchy. I apologize, everyone. It's having me go a little forward too fast here. I think it's widely understood that polyethylene and other plastics, for that matter, are very good for resisting the corrosive environment of a sanitary sewer pipe. And that entails hydrogen sulfide gas, sulfuric acid, etc. Now, there's a lot of very easily obtainable information on this topic. You can just Google it, and there's tons of chemical resistance tables and charts on polyethylene that you can see. But that's step one. So first, when you design for a pipeline, you're looking at performance, and then lastly, economics. But what are the performance criteria? And the first one is, can it handle the corrosive nature of it? And polyethylene does a very good job. Matter of fact, it's used quite often for relining products who are failing in that environment. So here's a kind of sum it all up from the sanitary sewer standpoint. You know, Eastern Idaho, over 10 years ago, has a very large trunk line interceptor being designed, and they're looking for solutions, and they're doing exactly what I think everyone on this call is trying to do. They're trying to limit how many times they lift it. It's a very flat installation. It's deep. It's in some locations pretty remote and kind of nasty area to work in. It's probably one of the coldest places I've ever been to in the United States during January. It's just Eastern Idaho, and it's 14 miles. So there's a lot of potential buildup of a biofilm and slime, etc. And Duramax was chosen. Nearly 7 miles of large diameter 48-inch was installed, 14 miles of product, including some PVC, and all of it was air tested. All of it was inspected, and it's done quite well. Now, this situation involved a couple different cover scenarios. As shallow as 15 feet, but as deep as 25 feet, I believe. So 14 miles of pipe, it's been in the ground for almost 15 years now, and has done extremely well. So that's the service life corrosive environment portion. Some other thoughts we had on top 3 concerns, and Brian, you might have to forward that. Mine's still not doing so hot.
Okay, I'll take over.
Yeah, and Ryan's going to talk to us about the second of our 3 design challenges, which is hydraulic efficiencies.
Well, and thank you, Andrew, and again, thank you for everybody for joining us. You know, the poll question that we took was very telling. Flat installations, and that's right now what we're going to really be talking about when we talk about hydraulic efficiencies, especially with that compared to other materials that you might be more familiar with. So with SRPE or Duramax, which is our family name for it, the hydraulics testing and like the structural testing that Andrew is going to talk about in a little bit, it's all done by third-party testing. And usually academia, there are other entities that'll do that. But in the case of our hydraulic capacity for Duramax, that testing was done at Utah State, which is one of the premier universities for this approach in the US. And what they do is they take about 200 feet of pipe and they run different amounts of water through it at different rates, and then they back calculate what the Manning's N is. So we were very conservative when we were doing this. Utah State was as well. And what they did is basically took realistic runs of water through the pipe and back calculated a Manning's N of anywhere between 0.011 and 0.013 with a recommendation to use 0.012. We could have run water through at a higher rate to get lower Manning's N, but it wasn't realistic, and it wasn't something that you're going to see in your designs. So we declined to do that. But at the end of the day, with a lot of entities, a lot of municipalities requiring the use of a Manning's N of either 0.012 or 0.013 anyway, we stuck with that testing and did not try to go any lower than that, just because most entities wouldn't allow us to use that in the first place. So we talked about the roughness of the pipe. That's one area where hydraulics are a loss. Another area is really inlet and outlet manholes and elbows. And we're going to talk a little bit about that here. You know, with sanitary sewer systems, you know, small diameters, a lot of entities, you'll get rid of those entrance and exit losses from your manholes by creating benching, and that's what you see here. So a contractor will come in, or even at the precaster. We've done this in manholes with prefabricated manholes out of our Duramax. Basically, you're creating one continuous channel through your manhole, thereby reducing or eliminating the losses that you see. So obviously in deep situations or very flat cover, everywhere where we can reduce the hydraulic losses is going to be beneficial. And you can do that very easily with small diameter pipe, like you see in the picture on the left, but how do you do that with large diameter pipe? It's not as simple. You're looking at manholes that might be as large as 120 inches in diameter. Creating benching through that can be a challenge. So it's one thing that we have done is really push and talked about the benefits of using a T-riser as opposed to a separate manhole. So that's what you see in the center picture. Obviously, the need for benching goes away because you're really just building the T-riser off the structure itself. And again, now you've got a consistent flow through the structure, quote unquote structure, but you really have access and just straight off the pipe itself. In talking to certain municipalities, some of them told me we want to keep the manholes, so we want separate structures. So another way to do that is what I'll call as a doghouse manhole. Basically, you're doing the same thing. You've got your pipe running through the section, and then you're creating the manhole on top of that. That pipe is then put in, grouted in place, and the top section of the pipe is cut off. So you keep your manhole, but you don't have to worry about post-applied benching or anything like that. So these are some areas from a hydraulic perspective that you can actually take advantage of and not have to reduce or worry about your shallow slopes that we're having to play with. Just in your designs. So the next slide I'll show you is a case history of that. This is a project that was in Montana, designed by Morrison Merrily, and it's Big Springs Ditch Water Users Association. So this is an irrigation ditch enclosure. Typical irrigation project, flat slopes like everybody was talking about, with having to move a lot of water. And in this case, hydraulically, we were looking at 54-inch diameter pipe that was needed, 3,000 feet. But instead of using a manhole, like a precast manhole structure or a cast-in-place manhole structure, Contech pre-manufactured the manhole access at our facility, and then the contractor would just install the pipe just like they normally would. So the bottom here, you show a detail off of our fabrication drawings. This is a normal bell spigot pipe, just with a 36-inch riser that was added on top at the plant. And for the contractor, the installation is no different than just installing normal pieces of pipe. So that's what you see in the pictures here, especially the lower picture. That's a shot inside the pipe with the manhole going up. So you can imagine we've got a lot of water flowing through here. Actually, this was designed to flow under low amounts of pressure. And so we pre-manufactured that riser So we don't have to worry about any types of losses or connections that are come through when we're attaching to a manhole. So the next thing that's associated with hydraulic efficiencies is really that of joints, and I consider them a subsection because that's the two really go hand in hand together. And we're going to look at joints from an inflow and infiltration. And for those of you who are new to I&I or inflow and infiltration, inflow is basically considered an illegal tap coming into a sanitary sewer system. So somebody puts their roof drain in and they illegally add that to by just making a connection to the pipe. That's inflow. Infiltration is really water coming in through the joints. So that's what we're going to spend more time talking about, because we can, through the design, we can affect infiltration much more than we can affect inflow from Contech's perspective. So this slide is showing you anytime that you have a joint, anytime you have a leak, no matter what type of pipe you have, obviously we're trying to minimize those, but if there is a leak, it's going to come, or there is infiltration, it's going to come from the joint most of the time. So if we can reduce the number of joints, your infiltration is going to be reduced just automatically without doing anything else with the design of the structure. So with SRPE, we're going to talk about two types of joints, welded coupler and bell and spigot. And our standard lengths are 24 footers for bell and spigot and 40 footers for welding. As a matter of fact, if we can do longer pieces, we will. And that, if we can reduce the amount of joints, we're going to be far better off from an infiltration standpoint compared to other systems you might be familiar with. Andrew talked about the steel in the pipe, and this is why we can get to larger diameters. If you remember anything from this presentation, it should be that the steel carries a load in Duramax steel reinforced pipe. We'll get to that in a little bit, but why that's important is it allows us to go deeper. It also allows us to go larger diameter. And the thing I'm going to talk about with our joints is that it's not just the steel in the pipe, it's the steel in the bells and the spigots as well. And the steel in the bells and spigots allows us to have a better, more controlled joint compared to that of a non-reinforced bell and spigot. So if you think about it, when a bell and spigot comes under pressure, the bell wants to expand and the spigot wants to contract. And that's why in non-reinforced joints, you start to see lack of intimate contact between the gasket and the bell and the spigot. Because we're using steel in the bell and the spigot, that allows us to use more consistent properties, something more solid to seat against for that double-seated gasket. And that's why it's so important to confirm that the steel in the bell and spigot as well makes Duramax a much tighter joint than you're more familiar with. So a case history I want to point out, and I'm going to push play a little bit, and then I'm going to hit pause real quick. So use this picture to kind of orientate you. Basically, this is going to be making of a joint. This is a 24-foot piece of 48-inch pipe that they're going to be making. And just as an aside, one of the comments that we get when people give us comments on our presentations is we don't do enough videos. So this is going to be a video. They're going to be homing the joint. And if you look in the lower left-hand corner, that's where the bell and spigot is. You see right where the gentleman is in the trench. There is a yellow homing joint. That's on all of our bell and spigot pipe. That tells the contractor when the spigot is made. They're going to be basically pulling from the upper right-hand corner with a sling attached to a track hoe. So it's a quick video, and I'm going to just push play here, and you'll get to see the joint made. So one quick push there, and then there'll be another push as the track hoe readjusts, and they just slide that 24-foot stick home, and they're done. So this was a project in California, multiple elbows, multiple sticks of pipe, and you can see how quickly, once the pipe joint is aligned, that they can make those joints and move on every 24 feet. So installation is much quicker than you might be involved with. So what if we have larger diameter pipe, or we're looking at a tank and we're looking for the tightest joint that we can make? And that's our welded coupler joint. The benefits of the welded coupler joint are, compared to other types of welded joints, is that it's done from the inside. And that means that the entire pipeline or the entire tank can be laid or installed and backfilled prior to the welding process. And that means the contractor does not have to wait for the welding process to occur. So the benefit here is, again, one of installation speed. The thing I'll point out here is just the welded coupler on the bottom, and then the sacrificial metal bands. Those metal bands, we get asked about those a lot. Those metal bands are basically an installation tool only. They keep the pipe aligned, and they also keep backfill from infiltrating through the joint prior to the welding. Once the welding is done, that metal band is just sacrificial. So case history I'll show. I always love to show case histories from my friends up in Canada. This is a project that they did in Humboldt, Saskatchewan, and it was a CSO storage tank. We do a lot of glycol storage tanks, a lot of CSO, and a lot of SSO, or sanitary sewer overflow storage. In this case, in Humboldt, it was a combined sewer overflow storage. So basically meaning during wet weather, when it rains, their sewer system gets inundated with additional water. So you can either allow it to flood, or you can allow it to be held part-time while the treatment plant catches up. And that's what the purpose of this tank is. 120-inch diameter, 560,000 gallons was the size of this tank, and all of it was welded and post-installation, and created the tightest tank that you can have outside of. The other location that we're going to talk about with inflow and infiltration, again, infiltration is the actual connections to the manholes themselves. So I alluded to this earlier, and we're going to kind of work from left to right on this slide. Basically, you have kind of a standard connection. Basically, we have two connections in the picture on the left. The bigger one is a grouted connection. The one on and then the other one is a booted connection. That's typically what you're going to see for most types of pipes. Obviously, you can get some infiltration through those joints or through those connections if that connection isn't made correctly. So to overcome that, we can use the doghouse manholes that I referred to earlier. Obviously, you really don't have a connection. You just have a single pipe going through an existing manhole. So you can reduce your infiltration there. And the best approach is really through riser manholes. So those riser manholes, again, same type of approach as a doghouse manhole, but you don't have a quote unquote connection to a separate structure, which again can increase, having a connection can increase the ability for infiltration to occur. So I think from a hydraulic perspective, that's going to wrap up that. Jill, before Andrew talks about structural integrity, I believe we have another poll question.
That's right, Ryan. Here's our next question. How serious is inflow and infiltration in your area? Is it not a problem, somewhat of a problem, a major issue, or you're not sure? I'll give you some time now to mark your selections. And just a reminder, type your questions in the question box, and I will ask them at the end of this presentation. And while you're answering our poll question, I just want to bring your attention to our handout section, where you can find some brochures for our wastewater products, Duramax brochure, our corrugated metal pipe brochure, just some things for you to look at after the presentation. I'll give you some more time now, just a little bit more time to mark your selections. And thank you for participating in our poll. It looks like 6% say it's not a problem, 46% say it's somewhat of a problem, 28% say it's a major issue, and 21% are not sure.
So those results, it seems like it is a problem. Very good. Thank you, Jill. And thank you, Ryan. Okay, Jill, you can hear me, correct?
Yes, I can hear you, but I can't see you.
Oh, don't know why. Okay, I'm gonna move on to structural integrity. We saw that as a design challenge, especially when it comes to just how do you get big diameter pipe in this corrosive environment, in this flat world with smooth hydraulic needs. And one of the big issues here is pretty deep covers. So this is a reminder, again, Duramax is more of a steel product than it is a thermoplastic. It has the benefits of both. The steel provides a modulus of elasticity of 29 million PSI. And I mentioned that because I'm just trying to compare it as far as its strength and its parameters per se. I call them performance parameters compared to polyethylene. Polyethylene has a modulus of elasticity of 110, 140,000 PSI. So there's a big difference between 29 million and 110,000. And that's why it is doing all the work. So don't take my word for it. Take the exhausting amount of testing we've done over the past 14 years. And I could say of all the pipe types in this segment of gravity world, I don't know of another product that has gone through as much testing as Duramax steel reinforced polyethylene has. We've worked through with AASHTO, and in fact, AASHTO agrees with us in the design methodology. So they have taken Duramax, and by the way, AASHTO is really the only gravity flow design methodology out there. And they have placed us into the steel section of the design manual, as well as the construction section. So it is not a traditional thermoplastic. It reacts more like a steel when it's tested. We've done a bunch of testing with probably one of the global experts out of Canada, Dr. Aaron Moore, and his laboratory testing 24, 60, and 120 inch in a soil box scenario. We've done a lot of third-party testing, universities, DOTs, and in the bottom right there, there's the non-ASTM sledgehammer test done by the Dallas maintenance group, who had just attached a tap onto the pipe. So they wanted to see how strong it was, and it did pass the sledgehammer test. So a lot of has gone into this material, and it does react, again, like I said, just another example of how it reacts under load. So, you know, what happens if we didn't have the steel reinforcement? Well, there's the potential of the weaker modulus, or more, call it fluid or viscoelastic material, liquid plastic, some people call it. The weak polyethylene could creep. This allows us not to need what's called a vertical arching factor applied for the pipe's height of cover tables, which basically means we're not relying on the product to circumferentially shorten on itself in order to shed some of that loading above it, which they do apply for some of the weaker pipe materials, and also means there's no inner wall buckling. I get that from time to time because when you look at Duramax, you're thinking black polyethylene pipe or polypropylene pipe, and is there going to be sort of wall buckling? Because that's important. And as we just discussed today, you know, we're deep, we're shallow, we have very shallow slopes. We don't want to change in our hydraulic Manning's end values and we don't want to see wall buckling. And Duramax does not have that issue, and it's primarily because, again, the steel's doing all the work, and therefore the polyethylene's along for the ride for all the good reasons. I did want to show the cover limitation. So this is a table just showing our diameter range. The minimum covers from 1 to 3 feet for ultra large diameter, 120 inch. But the maximum covers, you can see up to the right here, 50 feet for the smaller segment of the offering, 30 feet and 25 feet for the really big stuff. Now, that's our published numbers, and this is very conservative. We can and have and do go into greater burial depths than what's listed here. There's a large factor of safety on this value, and I think I have a great example of that next. So we're segueing into a case study here locally to our headquarters in Ohio, in the Cincinnati area. This was a Ohio DOT project. It was a combined sewer, so they're looking for something more resilient as far as a material choice. It was very deep. The maximum cover on this was 44 feet or more, and we did a Candy finite element analysis, and it checked out for 59. Now, it needed large diameters, ultra large, 72-inch sewer. And what we did with the engineer record and the contractor is Duramax was used for all the high fills, except where it was the very highest, which was where the 72-inch was going through a crossing and was somewhere around 44 feet. And what they did was they utilized a casing carrier pipe scenario, using metal pipe as the casing, and the Duramax was the carrier through it. And that's how they accomplished that one section. Now, this is right near downtown, right off Interstate 71 and MLK intersection, right in kind of the heart of the city. So very good project. Again, showing the abilities of what a steel reinforced material can do for polyethylene in very deep depths. And that's the environment that and that's a challenge, I think, for a lot of people in sewers. So, a good example of what 10-foot looks like. Those of you who haven't been by a basketball hoop lately, here's 120 inches of very big pipe, and not easy to develop from a pipe standpoint. And that's kind of segues us into real fast. I want to just briefly discuss the development of Duramax. It's been around in Australia and Asia for many decades now, and Contech brought the technology to the United States in around 2007-8, and we began making pipe. And we built Duramax a little differently than what was done in Asia. We made it to address a lot of the markets here in the United States. It's designated under ASTM F2562. Again, we get 14 years of in-ground performance in the U.S., millions of feet of pipe installed, and this includes from New York City to Guam. Literally, we've done projects in Guam, and from Canada down into Mexico. So a lot of product out there, a lot of good projects for us. So the manufacturing process. It begins with extrusion of the profile itself. And I do this just so everyone can see real quick how we make it and understand it a little bit further. From after the extrusion, we insert steel ribs. And that's the second process. The third process is we fully encapsulate those ribs. We put a cap on the top. Now this 80 KSI steel is fully encapsulated, and we wind it onto spools, kind of like you see like a large fishing line, so to speak. Now this is done in Montgomery, Alabama, and we have winding facilities in Montgomery and Ogden, Utah, but it's all American made. It has a delay. It makes me go too advanced. I again apologize to everyone. After we've spooled it, we can ship that spool across the country to Ogden or wherever we have a winding facility. And from that point, we're going to make it into the pipe. So we despool the material from the winder, and we insert it into a controlled environment and a winding cage. And that cage is where we do the fusion welded process itself. Now this is very high-tech type of manufacturing. For those who are used to going to a pipe manufacturing facility, a lot of times there are various types of pipe manufacturing products. They're pretty dirty and dusty, and this is a very clean and precise type of manufacturing. It's pretty cool to see, and if anyone wants to come to our facilities and see this firsthand, we'd love to invite you. After it's been welded together, is then cut, and then we can take it off and put on the bells and spigots or whatever else we want to do with it. One of the beauties of polyethylene and steel is that it's very easy to fabricate with, meaning we can weld and do a lot of versatile type of fabrication scenarios, and therefore a lot of versatility in the design. So it's very fabrication friendly. We offer a full line of elbows, tees, risers, all the standard stuff to the industry. A lot of the welding processes is overseen by a very robust QA, QC type of procedures. We have spark testing methods that we can use to check welds. I do want to note that when we do weld the pipe together, the welds themselves are stronger than actual pipe material, and we go through various tests to ensure that. So overall, versatility of Duramax, it means we've participated in a lot of different applications. Sanitary sewers, wastewater treatment plant, conveyance, outfalls, various chambers for wastewater treatment plants, low head irrigation, very critical storm sewers, reline, underground storage, et cetera, et cetera. And so a great example, we've mentioned a few times now CSO storage, and it's interesting because it involves all the aspects of everything we've been talking about. Ultra large diameters, sometimes multiple diameters are used to create a very large underground storage system. This is nearly 700,000 gallons of storage. It was 120 inch. Its invert was 30 feet below grade, down into a very deep and steep, I'll call it a hole in the urban area of Cincinnati again. Very difficult work site, and it would have been problematic to use a crane or other traditional methods of installing precast or cast in place type concrete structures, etc. So working with AECOM and again, the MSD of Cincinnati, Duramax was used. Risers were done 20 feet up to gain access. Again, looking for something that was inert to the environment, structurally strong, and could be very watertight to deal with all the scenarios here in this case study. Ryan, I think you should probably take control at this point because it just does not want to forward for me.
Yeah, no problem. The joys of technologies. We've got to get so far, but there's still some trade-offs. So I'll take the next 10 minutes kind of talking about the final constraints that we've seen for job sites, and then go over some questions and answers that hopefully Jill will be able to help with. So, you know, Andrew was talking a lot about, and actually one of his slides showed the lightweight of Duramax compared to that of other products. And some of the case histories I'll show you will use that as a benefit, but you know, one of the drawbacks you can get from time to time with the lightweight material is that of buoyancy. So, you know, a lot of the you know, yard piping that we do, even piping to a water reclamation facility or at a water reclamation facility, you know, these places are usually at right at the or have high groundwater elevation, low elevation in terms of height of cover, and those two things can really create a problem if for a lighter material such as steel reinforced polyethylene. So we do run into questions about potential buoyancy. We do have rules of thumb. That's the chart that you see here for the amount of cover needed to prevent flotation, and that's assuming an empty pipe. So the joints are doing their job. We have great joints. They're doing their job. They're not allowing water to come in through infiltration. And if the pipe's empty and you have high groundwater elevation, that needs to be analyzed and reviewed. So rules of thumb are a great tool. That's what we have here, but every job needs to be looked at separately because it's just better off to make sure if there are buoyancy considerations, how to overcome them. So looking at this, what we look at in a single pipe application, this is one of those projects that Andrew mentioned is on Guam. It's at Andersen Air Force Base. And you look at the high groundwater elevation and then the soil that's weighing the pipe down and how much soil is needed. Here we're able to use kind of a continuous wedge over the top of the crown of the pipe that's going to be able to take into account the effect of weighing down that pipe. But let's say you have a tank like Andrew's last case history, and you've got two pipes right next to each other. You can't actually take a wedge, and because you're accounting for that wedge twice over these pipes. So in those situations, we are looking at only the pipe or the soil directly over the pipe itself as a hold down. It's a little more conservative, but it is probably the best approach that we want to take. So obviously we need more height to cover on a tank than we would on a straight run of pipe, a single run of pipe. So these calculations that you show here, basically what we're doing is we're calculating the amount of displacement that is used in the by the high groundwater elevation, and if that buoyant force is greater than the amount of soil that you have holding the pipe down, we need to add more force. So that can be done either through soil anchors, it could be done through dead bend anchors, special backfills. We've seen it all. We can help coach through that. We don't really come up with a design for the specific hold down, but a lot of times we are engaged in determining, okay, here's how much hold down we need per foot of pipe. There are third-party companies that manufacture soil anchors that can help with a specific design, or if you're using pure weight, that you can do that as well. So the case histories I have about that, one is in Utah, Ephraim City Wastewater Improvements, and this was a chlorine contact chamber. And you know, when we run into chlorine contact chambers, usually they're larger diameter than what you see here, but in this case, it was 48-inch diameter that they had. And again, we're at the water treatment facility and high groundwater elevation, not a lot of cover available. So those two things combined to add up to, we had some buoyancy concerns that we needed to overcome. In this case, they actually poured a concrete slab over the pipe to act as a hold down. That was one approach out of a couple that were taking considered. This one was the one that was used. Another project in Washington State. I love this project for so many reasons, just because we created a lot of fittings inside of it to create low flow channel inside where the contractor in a normal pipe would normally have to create benching. We actually pre-manufactured the benching to account for a low flow channel during dry weather events, but during wet weather events, the entire volume of this 84-inch pipe was used. Again, just like the previous case history, we had a high groundwater elevation, and so they actually used a slab underneath the tank. And you can see in the picture on the right, that yellow strapping, that's the strapping that is tied into the concrete slab underneath this tank. So just another approach that we worked with the design engineer to do. So getting back to the benefit of the high or the low weight per foot of the pipe. This is a project that's actually being installed right now in Des Moines, Iowa. And they're replacing an old storm sewer and actually enclosing parts of a ditch in another area. So the yellow area in the map that you see, that is the area of storage. So they're stockpiling the pipe there. And then you can kind of see the stream going down, and the green area, that's where they're going to start enclosing, or where they have started enclosing the ditch. And then they're going to continue that line further south as the map is oriented. So with the Duramax, what they were able to do is actually track each piece into place. You've got a business and people's yards in this green area that they could not stockpile pipe. So they had to track each piece from the staging area into place. So very tight area. And you can imagine if they were to do that, say with a heavier pipe, one, you'd need a bigger piece of equipment, but two, you'd be tracking every 6 foot sections or 8 foot sections as opposed to a 24-foot section. So this job really aligned itself to be one used for a Duramax steel reinforced pipe. The last case history I'll share with you is Sunrise Douglas. This is a sanitary sewer project in California, and they had 4 hours worth of overflow that they had to account for, and they did that with this pre-manufactured tank. You gotta love working from home, everybody. Listen to my dog. So I'm gonna wrap up just with the resources that you have available to you. Obviously, you have Andrew and me. We'll have our points of contact coming up on the next slide, but I also want to point out and reiterate what Andrew said about our website, www.contechs.com. A lot of standard details there, a lot of case histories that you can find, and then many PDH articles. This webinar will be posted there as well. So just want to reiterate that and leave you with the last slide with Andrew and my points of contact. And I want to thank everybody for your time, and hopefully in advance for the good questions that Jill is going to take us through as we have a few minutes to spare. Jill?
That's right, we have great questions. If you have a question, type it in the box. Our first question is, what is the minimum cover needed for the Duramax to handle highway loads?
That's a good question. And you want me to take that?
Sure.
Yeah, so it depends on the diameter. We do have standard details for this. So for the smaller diameters of pipe, for highway loads, we need 1 foot. So that's up through 60 inch. If you get to our larger diameter pipe, say 120 inch, you would need 3 feet for highway loads. So, and to build on that question, if you have rail loads or airport loads or anything like that, we can work with you to determine what those are. Good question.
Next question is, how do you test the SRPE after it is installed?
I'm going to assume, I'll take that one, Ryan. I'm going to assume testing, we get asked that question quite often, and I'm assuming they're talking about the joints. So if the question's about joints, the small diameters, well, the easiest way to answer that is, how are you testing the pipes that are using today? Whether it's concrete, ductile iron, fiberglass, whatever, PVC, we're going to test the same way. So we're using the same methodologies with low head pressure testing. It's very rare to see hydrostatic testing being done with water, unless you're in a tank environment, but we're following the same industry standards everyone else is doing. That's the easiest way of answering that. If you want some more information, we can be happy to supply it, or even help recommend something based off of the project's parameters and what's going on.
Thank you, Andrew. We have time for one last question. Can the SRPE be used in pressure applications?
Yeah, I can address that. Everything that we talked about today has really been geared towards gravity flow. with few exceptions. We can handle low degrees of pressure with Duramax. And when I say low, it's depending on diameter, but 15 PSI or less, that would be something that that Duramax would be a potential fit for. Anything above that, that's not going to be something that we would really be trying to address via Duramax.
Thank you, Ryan. I just want to call everyone's attention to the chat box. I popped up the registration link for our upcoming stormwater webinar. That's Wednesday, March 23rd at 2 p.m. Eastern. And then I also put in the registration link for part 2 of our infrastructure webinar on pipe solutions, the answers to aging infrastructure challenges, when to reline aging and failing culverts and sewers. And that one is Thursday, April 28th at 11 a.m. Eastern. So I just want to thank Ryan and Andrew, and thank you everyone for participating in today's webinar. If your question was not answered, don't worry. Andrew or Ryan will reach out to you. They'll have the answer. They'll get to you in a timely manner. I know we didn't have a lot of time for questions, but they will answer your questions. A survey will appear once we conclude the webinar. Please complete the short survey to receive your PDH credit. A follow-up email will be sent by the end of the day that will include a link with instructions on how to download your PDH certificate. And then I'll send the link again to register for part 2. So if you didn't get a chance to do it now, you have time later. So that concludes today's webinar. Thank you again for joining us and have a great day.
Bye, everybody. Thank you.
Thank you.